Friends, welcome back to the physical enjoyment. So we are now going to see the another three basics of the electricity, and which are the Gauss's equation, the Laplacian equation, and the Poisson's equation. So first of all, we are going with the Gauss's equation, the Gauss's theorem. First of all, we will see the statement of this theorem. So this theorem states that the electric flux or the flux in free space through a closed surface is equal to 1 by epsilon naught times the total electric charge enclosed by a closed surface. It means we have one surface which is closed surface, and there is charge distribution, which is the charges are positive and negative. So the total electric flux phi E will be as we know E into ds, surface integration of electric field, and it is also equal to Q by epsilon naught. It means 1 by epsilon naught times the total electric charge enclosed by the surface. So it was only the theorem and the statement. Now we will prove this theorem. So how to prove? For that we will consider one 3 coordinate axis x, y and z. O is the origin of this coordinate axis. Okay. Now we will put one point charge Q on this origin. So there will be electric field around this charge, and for consider it, I will draw a closed surface S, which is Gaussian surface. Okay. Now to determine the electric flux, I will draw a small element of surface on this closed surface, which is at the vector distance r from the origin. Okay, so it is the ds. ds is the area vector, and which is equal to ds into n cap. So here, as we know, what will be the electric flux? So electric flux, which is d phi, that will be E into ds. It is the integration of this E into ds. These both are vector quantities. Okay, what is E? E is the electric field. So how can I write E? That is kq upon r square into r cap. That is nothing but 1 upon 4 pi epsilon q upon r square into r cap. Okay, and ds, that is the value of this vector, that is ds and n caret. That is the direction of this area vector. Okay, so now the total flux for this closed surface will be 5, and that is the integration of this d phi. It means we have the small ds over this surface, and we will integrate this to the closed surface. It means we are continuing adding this ds plus ds plus ds plus ds, and we will get the final total surface, and for that we will calculate the total electric flux. So total electric flux will be integration of d phi, that will be the surface closed integration of vector E into ds, because it is a closed surface. So I will put this value in this equation. I will get 1 upon 4 pi epsilon naught q upon r square into ds is ds into r cap into n cap. So here r cap into n cap, that is nothing but that is the cos theta. So I will write here 1 upon 4 pi epsilon naught q by r square ds cos theta. So here this is the vector r, and here for ds we can consider one cone. Okay, and these electric field lines are the sides of this cone. So here ds cos theta upon r square, that is the area upon r square, and that is nothing but that is the solid angle, and this solid angle here ds cos theta upon r square. Okay, this is the theta. So this solid angle is here subtended by this ds at the origin point or at the q. Okay, so ds cos theta upon r square I can write omega. So this equation will be 1 upon 4 pi epsilon naught q upon r square into omega. So these are the constant quantities, and for that I will write 1 upon 4 pi epsilon naught into q, and here the summation of omega. So omega, which is solid angle, so for a closed surface the omega, the value of omega is 4 pi. Okay, so I will substitute value in this equation. I will get q by epsilon naught. Okay, because 4 by 4 pi will be cancelled out. So q by epsilon naught, that will equal to 5e. Okay, and this is the flux, total electric flux from a closed surface. So we have proved this equation. Simply we have proved it. So now we have two equations. The surface integration of E into ds, okay, for flux 5, and which is also equal to q by epsilon naught. So this equation is called as the integral form of the Gauss's equation. So now we know that if I want the flux in this small volume, for this small volume t tau, which is d tau, I want the flux which is passing out from this small element volume. So what will I to do? So I have this equation. It means I have flux divided by this volume. It will give me the total flux passing by this small volume. So that will have E into ds upon d tau. This equation, as we know that it is nothing but it is the divergence of E, and that is equal to q by epsilon naught. Here there will be a small amount of q in this small volume, so I will write dq, and I will divide by it dt, so it will be rho by epsilon naught. So here what is rho? So rho is the charge, volume charge density. Okay, so I have got this equation 5e, that is equal to E into ds, that is q by epsilon naught. and the another equation, divergence of E, that is rho by epsilon naught. Okay, so it was the statement and the proof of the Gauss's equation. Now I will see the three cases from this equation. Before I go for this equation, I would like to clear that what is the total charge enclosed by the surface. So suppose I have this surface, closed surface, and here are many charges, positive and negative charges. Okay, so what here, Q1, Q2, Q3, Q1, Q2, Q3, these are the positive charges and these are the negative charges. So what will be the flux from this charge? So that will be Q1 by epsilon naught, Q2 by epsilon naught, and Q3 by epsilon naught, plus so on. And for this, Q1 by minus Q2 by epsilon, minus Q2 by minus Q3 by epsilon naught, minus so on. Okay, so what will be the total flux due to positive charges? So flux from positive charges, that will be Q1 by epsilon naught plus Q2 by epsilon naught plus Q3 by epsilon naught plus so on. That is 1 upon epsilon naught and the summation of Q I1 to N. Okay, so it will be the flux for the positive charge. And what will be the flux for the negative charge? That will be Q1 by epsilon naught. I will write Q1 prime, Q2 prime by epsilon naught, and Q3 prime by epsilon naught. So it is 1 upon epsilon naught, Q1 prime minus Q2 prime minus Q3 prime. So that will be 1 upon epsilon naught and the summation of negative Q from 1 to N. So what will be the final and the total flux? That will be 5 from positive plus 5 from negative. That is 1 upon epsilon Q I is equal to 1 to N plus 1 upon epsilon naught negative charge I is equal to 1 by N. It means 1 upon E into total charge I is equal to 1 by N. So what I get? Here I get that the total flux enclosed by a surface, it is equal to 1 by epsilon naught times the total electric charge. It means the summation of the charge, and it is the algebraic summation of this charge. So it was just clearance of this the total electric charge enclosed by the surface. So we will see the another three cases related to this Gaussian theorem. So first is when charge is outside the surface. So what happened in this case? So we have one closed surface and here I have positive Q charge here. So what will be the flux from this point in this closed surface? So here we know there is no charge enclosed by the surface. It means there is not any total charge enclosed by the surface. It means Q is equal to 0, and from that Q will be Q by epsilon naught, that is also 0. So here the flux coming inside will equal to flux going outward. Okay, so it was the first case from this equation. Now we will see the second case. To see the second case, I will like to draw a surface like this. Okay, now in start I have a point A here and it has a positive Q charge. So there will be the flux lines coming outside from this charge, and this charge, these field lines are going from this way, and the another is this way. Okay, these two are the field lines. So here how many surfaces are cut by this flux? So here it is the ds1, here it is ds2, here it is ds3, here ds4, and here the ds5. So these are the 5 surfaces through which the field lines are passing. So what is for this first surface which is ds1? So for this first surface which is ds1, as we know, the flux coming outside of any surface is positive. So here the flux will be positive. For ds2, the flux is going inside, it means it will be negative. For ds3, what is for ds3? It is coming outside, coming outward from this surface area, so it will be positive. Similarly, ds4 will be negative, and ds5, these are the values of flux. This ds5, here flux is coming outward from this surface element, so it will be positive. So what will be the total flux? So total flux is nothing but the summation of the flux, that is the positive flux, positive, negative, positive, negative. So the q by I will q by 4 pi epsilon naught into omega. So for first it is positive, then negative, then positive, then negative, then positive. So positive, negative cut. So I will get final by 4 pi epsilon naught. So it is the total flux. It means there is a certain value of the flux when the field lines crosses these surfaces in a odd number. So here we have one simply consideration that when field lines passing through these surfaces which are in odd numbers, so there will be certain value of flux. But suppose I have a point outside this surface, okay, so what will be the field lines? Suppose it's like that. So these are the field lines. So here it is the first, second, third and fourth. So for this, ds1 will be negative, ds2, ds3 and ds4. So for the flux, ds1 will be negative, for second it will be positive, for third it will be negative, and for fourth it will be positive. Okay, so total flux will be 0 because it will be cancelled out. So total flux is 0. It means when a charge is lying outside the surface and the field line cuts the surfaces in the even number, so there is no net electric flux or electric field lines per unit area, that will be 0. Okay, so it was the second case, and from the second case we can also prove this, that when the charge is outside the surface there is the not electric flux. Okay, so now we will see the third case. In third case we will take the electric dipole. So what is the dipole? So as we know, when the two charges of equal amount, it means equal magnitude but opposite sign, are placed very near to each other, and it forms a electric dipole. So now I will put this electric dipole in a closed surface. So what will be the total charge for this closed surface, in the closed surface? So that will be positive q, negative q, that is 0. So therefore flux will be 0. Okay, here flux is equal to q by epsilon naught, that is E into ds, that will be 0. So here it does not mean that here E into ds is equal to 0, it means there is not any electric field due to this electric dipole. Generally positive and negative, so there will be field lines outward this from here and here, and negative, the field lines are coming inward direction. So on a particular surface, there is the fixed and the definite value of the electric field on the surface. Okay, so it is the simple thing that you have to remind, that it is not necessary that there is the total electric field is 0 when flux is 0. Okay, so it was the Gauss's theorem. So now we will see the Poisson's equation and the Laplacian equation. So first we will see the Poisson's equation. Okay, so generally we have one equation, E is equal to minus gradient of V. V is nothing but it is the electric potential. So one can define electric field in the terms of electric potential, which is E is minus grade V. So I can write this minus grade for V. There are three components for V, and which is del V upon del X plus del V upon del Y plus del V upon del Z, I cap, J cap and K cap. So it is the E, it means electric field. Okay, so now from this equation I can say that the X component of electric field Ex, which is dVi upon dx, the Y component, that is dV upon dy into j cap, and Ez, that is del V upon del Z into k cap. Okay, so from this equation I can say this equation first. So what will the divergence of E? So divergence of E, that is del E upon del X plus del E upon del Y and del Ez upon del Z. So I can put this value in this equation, and finally I got del Ex upon X, so del X into X component, which is del V upon del X plus del upon del Y into del V upon del Y plus del upon del Z into del V upon del Z. So it will be del square V upon del X square plus del square V upon del V del Y square plus del square V upon del Z square. So it is the divergence of E. Okay, so here I have del square upon del X square plus del square upon del Y square and del square upon del Z square. So it is known as the Laplacian operator or the nebula square. It is the nebula and it is called as the Laplacian operator. Okay, so I can write here nebula square into V. Okay, so it is the equation, and here all have negative. So here also will be negative. So it is the equation for the electric field, divergence of E, that is equal to minus del square V. Okay, so from the Gaussian equation I know that what is del square V, that is 4 pi rho. Okay, so I will put this value in this equation and I will get the divergence of E, that is minus 4 pi rho. So I can write the Gaussian equation in this term. So if I write from this equation, it will be del square V upon del x square plus del square V upon del y square plus del square V upon del z square, that is minus 4 pi rho. So from this equation I can say that one can determine the value of the electric potential, okay, by summing the contribution of each component. It means I have point x, y, z, and here there will be the certain value of potential, electric potential. So when I will sum up this for x component, y and z component, I will get the total, I will get divergence of E, or I will get the total electric potential at that point. So this equation is called as the Poisson's equation. Okay, so it is the Poisson's equation. Now when there is in free space, when there is no charge enclosed by surface, it means there will be rho is equal to 0. Rho is nothing but it is the charge volume density. It will be 0. So rho will be 0. So here what will be divergence of E? It's equal to minus nebula square V, that will be 0. So it is called as the Laplace equation. Okay, so it is the Laplacian equation. Now there is one function, it means if there is V, X, Y, Z, which will satisfy this condition. Okay, so it is known as the harmonic function. And in physics it is very important to find out the harmonic function. Okay, so it is, now we have seen all the three basic of the electricity, which are the Gaussian equation, the Poisson's equation, and the third, the Laplacian equation. So meet you in the next lecture.